All right.
Thank you again, Professor. You enjoy this conversation with John Platt to StormForge for Demystifying your Kubernetes resource management.
Hey, thanks for coming, everyone. My name's John Platt. I'm the CTO at StormForge. We're a small company, about 30, 40 people. We have a product which optimizes resources on Kubernetes using machine learning. My background's applied maths, machine learning, but I've been working with Kubernetes for sort of 5 years, so pretty familiar. And how Kubernetes manages resource is kind of our sweet spot. So it won't be a sales pitch, but we would like to think of ourselves as one of the experts in this area. So just to start, how many people have sort of experience with Kubernetes? Oh, so most people. Okay, great. Hey, fantastic. Then hopefully I've set the material at sort of the right sort of level. So first, before we dive into the details, why people need to care about resource management on Kubernetes. And there's a few different reasons. If you don't set your resources correctly, you're going to end up having performance and reliability issues. Everything's going to go down, which obviously no one's fine with. Once you start setting them, if you don't set them correctly, it's going to be extremely expensive because you run on AWS, you run in the cloud. If you request 20 large servers, you pay for 20 large servers, even if you don't actually use them. So actually requesting the right resources is key to actually running efficiently and not blowing budgets. And then finally, once you actually start to scale up, you've done your sort of trials with Kubernetes, etc. You want to start migrating a large number of workloads to it, having proper isolation of those workloads on a cluster so that you can manage it without lots of noise, workloads interfering with each other, and manual tasks driven by developers who maybe know a little less about Kubernetes. We see people drown in that all the time. So the talk structured sort of from the inside out. First, single container point of view. How do you isolate resources for one container, one pod? Then the second part is, okay, you have a whole bunch of pods on a cluster. How do the resources set on the individual containers interact with the rest of Kubernetes? And then finally, the actual sort of policies to manage it at scale on the processes. Kubernetes comes with some built-ins which help, but don't necessarily fix everything. So let's start with the individual container. So how many people have heard of requests and limits? So about half. So these are the sort of building blocks of Kubernetes resource management. You go in and you set requests and limits on individual containers. And the way it works is the request is the minimum resource that container is guaranteed to get. So if you have, the way Kubernetes works is you have a node. So a node could be running 40, 50 containers. And you need to make sure that when you go to share the resources on that node between those containers, everyone gets their fair share. So when you set the request, that's the minimum you're guaranteed to get. The second sort of building block built into Kubernetes is limits. So the limits are the maximum you're ever going to be allowed to get. So you can set limits, and what that'll do is prevent, if you have a node with 40 or 50 containers, it'll stop one container running away, sucking up all the resources on that node, and then bringing everything else down and breaking everything else. And you can set requests and limits for a few things. The ones everyone uses is CPU and memory, the two main sort of compute resources. There's a ephemeral storage, which lets you grab storage on the node, used now and then for certain things. And then it's extensible. So you can have extended resources, unusual use case. People define their own, maybe it's GPUs, and you want to be able to say, this workload needs 1 GPU, this workload needs 2 GPUs. But typically it's CPU and memory. And you can see down at the bottom right, what it looks like in YAML, because as with all things Kubernetes, it's just YAML everywhere. Yeah, question.
Is that limit per cluster, per container?
Per container. So all requests and limits and all resources are managed at the container level. So if you have a pod with 4 containers in it, then you need to set the resources on each of those containers individually, which is a good thing, because if you have 4 containers each doing a totally different thing, a one-size-fits-all approach doesn't make sense.
And that depends on the size of a cluster, right? So it can only grab as much as you assign to the cluster.
I'll get into the cluster later. This is just at the individual container level. The way you're typically thinking about this is what is the application actually doing and what sort of load is on it. So say it's a machine learning application which requires a lot of compute, maybe you'll need a lot of CPU. Maybe it's an application which is very spiky and does a lot of stuff around lunchtime, but not a lot in the evening. And then the question is, do you want to provision for the peak, the trough? There's a few different things, but it's typically how much load is on it, what's it doing, etc. And then the little graphic on the right is on the left is meant to highlight that sort of dark green, the requests, you're guaranteed to get that. That's what you can rely on. And then the light green, which is the space between the requests and the limits. If you've set the request to be 250 millicores and the limits to be 500 millicores, that's what you can burst into. So it's the resources you can take if no one else has requested them, but you can't rely on them because you're not guaranteed to have them. So is that, how many people roughly knew that already? Yeah. How many people know how requests and limits actually work under the hood with the kubelet? Yeah, there we go. See, a lot of people use them. Not a lot of people know what's happening underneath. So the way it works underneath is the kubelet has, the job of the kubelet is the agent which runs on every single node of a Kubernetes cluster and manages the containers. And the sort of Linux package or tool that it uses to isolate resources is called cgroup. Right, the default, the standard that Kubernetes first shipped with was cgroup v1. They've been migrating, apparently v2 came out, and then Kubernetes has been bringing it in. It was stable in Kubernetes in v1.25, so recently. And I don't think it's rolled out across all the big cloud providers yet, but it's coming soon. I'm going to focus on how it works for v1 just because it's the standard and it's the one I know because I haven't looked at I haven't looked at the new one in as much detail yet. So cgroup manages the CPU and the memory. I'm going to focus more on the CPU. So inside cgroup, there's something called the CFS, completely fair scheduler, which decides how different processes get access to the CPUs on the node. So this is built into Linux, and then the role of the kubelet is to configure the CFS. So it's just using the underlying Linux tools, and the kubelet configures them. And the two sort of entry points, or the things that the kubelet works with, are called CFS shares and CFS quota. So requests get translated into CFS shares. And what that's basically doing is saying, okay, I want X shares on this CPU. And then the CFS is going to go in. It's going to say, okay, of everyone who wants something, how many requests or how many people have put in for shares? It's then going to sum all of those up and say, okay, this person has 25% of the shares. This person has 50% of the shares. How many CPUs do I have? And then each person is softly limited to that. So I have a worked example here. So the idea is you have a node with 2000 millicores. You have 4 different containers running on it with different requests. So the requests for the 4 containers are 150 millicores, 150 millicores. The machine learning takes a lot more compute, so it's 500, and the cache takes 250. So then the CFS shares, it takes the millicores and multiplies it by 1024. So they look very similar to what the requests are in millicores. And then, so 1 second, let me just move that. If we were to sum up all of this CFS shares and figure out the fraction of the node that each one has, you're going to have 14% for the first 2, 48% for the machine learning, and then 24% for the cache. And then when you go in and look at the actual guaranteed CPU each of those gets, you end up with numbers which are significantly more than the actual requests. So the idea is when it translates it, it's not direct. What it says is, okay, everyone, if the node utilization, if the requests were 2000 millicores, then If you requested 150, there's no free space on the node, you will get 150. However, if there is unused space, it's not Kubernetes is not going to waste it. It's going to apportion it out to all the workloads depending on the requests they have, because that's what translates to the CFS shares. So that's how requests work. The limits are converted into a different CFS concept called quota. So the quotas say, okay, I'm going to sort of, I have X cores on a node. I have different time slices, and I'm going to actually allocate different processes, different slices on the CPU. And it keeps track and says, okay, if you can't use more than 500 millicores, that means you don't get to use more than this number of slices. And it will actually go in and stop the scheduler giving it more than that. So I think there's a period, I can't remember exactly what it is, around a second. If you've used up all of your slices, you just wait. Even if the CPU is idle, you have to wait until it resets. And then you can go again until you hit your quota, and then you get paused again. And then you can go again until you get paused again. And you can see that CPU throttling in the metrics coming out of the kubelet. I think I can show it in a moment. So that's CPU. Memory is simpler. The kubelet does nothing, or the C groups does nothing with the memory requests, completely unused. And the memory limits get configured into a maximum, which if you hit, the pod or the process gets unkilled. So much, much simpler than CPU, which probably makes sense because sharing out the resource maybe is a little bit easier to do. Questions? Yeah.
Is there some sort of like a formula of how it come up with the percentage?
Yeah, I should have put the maths on. I have a maths background, so I love putting equations in slides. And then everyone always tells me people hate the equations, so I take them out. The formula is take the second row, so all of the shares. That's the total number of shares like people have put in for. Sum them all up, and then the amount you get is your shares divided by the total. So I got to that 14% by summing up that row and then dividing 153 by 300, 800, 1050. And then the leftover space is shared out equally between everyone, which is why you get the almost double the requests for every workload.
So where do you get the 2000 cores to assign to the Kubernetes?
So that's when
EC2.
that's a VM, which is going to then share its resources between all the containers running on that node.
So you're hypervising that one EC2, or are you hypervising a set of EC2s?
There's a few different ways it could be done. The worker nodes could be VMs, they could be bare metal, they could be running in the cloud, they could be running in the data center.
Okay.
To Kubernetes, it's not that Kubernetes doesn't care because things will run differently with different hardware, but the idea is that each node with Kubernetes, you install the kubelet, you have a node which already exists, and then the kubelet is going to report back the size of that node to the Kubernetes API server, and then the API server will share it out between the different containers.
So what are the relationship?
Sorry, what's the relationship? It's you take the requests, divide it by 1,000, and multiply it by 1024. So 1,024. It just takes it from.
I mean, is that at the network level, or is that?
No, it's done inside. It's done inside the kubelet.
So a request is a concept as a construct within Kubernetes.
Exactly, 100%. Yeah. Requests is the concept inside Kubernetes. Limits is also a Kubernetes construct, and then it gets translated into a form that C groups can use, or C group can use, and that's what isolates resource on the actual node between the different containers. Yeah. Yeah.
For CPU, just throttles, it slows down, but the memory, it's killed. But when you kill a pod in Kubernetes, that means a fresh one is born to replace it.
I mean, but you're layering hypervisor over hypervisor, right? So there's AWS and then there's Kubernetes. Then AWS does the throttling underneath of it too. So there's like, a lot of throttling there, unless of course if you get resource assignment and then you have that range.
You're the one setting the limit. And you set the limit to say, please don't run away with this. Something's very wrong if you go this far. So it's self-inflicted. If you hit that and it starts with you just increase, it's sort of, you're worried that it might be ill-behaved and take over the machine or something, so you could do it. Some kinds of endless loops and problems like that.
Any other questions before I move on? Okay, let's go then. Okay, so it's one thing to say it. I thought it might be fun to actually see it. So I have a mini demonstration. Anyone, is that too small? People see this? Okay, perfect. So I have a cluster running in AWS. It's got a single node. Let's see. A single node, and the node has a capacity of 2 cores. That's where the 2000M from the previous example came from. So it's got 2 cores. There's a small amount of overhead for the kubelet, so the amount left to actually share out between the different user workloads is 1930 millicores. And then let's actually pick that up. Practice.
YAML, right? That answer.
Oh, this is all YAML.
So how do you find out the allocatable resource amount without running in it? Is it somewhere on the AWS side that they provide this on each node type?
Oh, yeah. If you go in, you would pick a node type, and then the node type would dictate the capacity. If you
The allocatable.
So the allocatable is just the node type minus a kubelet overhead. If you're using EKS, they are configuring the nodes for you. And
How it comps?
you would probably have the ability to change that yourself.
It's under status, so that's the telemetry coming off. It's gonna be changing it as the cluster.
No, but
Allocatable doesn't change. It's just the amount left after the kubelet overhead. But you're probably, if you're running the cluster.
Scaling,
I'm asking from the architecture point of view.
Yeah.
You're running you're planning to design a new cluster.
Yeah.
How would you find out the allocatable CPU on particular node type?
I imagine this isn't a thing I do. I don't run the clusters. We work mostly with people who are running in the cloud with a managed cluster. I imagine COPS has a place that you can configure how much overhead to save for the kubelet. And then what's going to happen is whatever the size of that node is, it's going to subtract that. But I don't know them. I'm sure there's best practices and guidelines about how much to reserve from each node to run the kubelet.
Oh, so you're saying kubelet has a fixed size that it can get. Okay.
It's a configurable one on EKS. I
But
think
there
it's
isn't-
fixed. Yeah.
Based on the server you're installing, right?
It's the server minus what it takes to install Kubernetes itself, and then everything else is a blank slate for containers to be scheduled into.
So I have a node about 2 cores running, and then I have Prometheus running to collect metrics, and so we can look at what actually happens as the workloads run. And then where am I? Here we go. I have 3 workloads, and the 3 different workloads. We have one which sets no resources. We have one which sets just requests. You can see down here. So this is one which is guaranteed to get at least something, but it has no limits on it. It can run away as far as it wants. And then we have one which is limited. So it's the same as before. Only this time, once it hits 1,000 millicores, it's gonna stop. And all three of these are running a resource consumer image. It's an image or like a small package built into Kubernetes. It's typically used for testing. What it does is it sits there and you can get it to just consume a fixed amount of CPU. So it's good for testing, auto scaling, generating fake load on clusters, etc. And I'm gonna, let's see. I'm gonna create the 3 workloads. So you can see 3 deployments got created. And then I'm gonna, let's see. Create so this is gonna tell it to consume 450 millicores. So each of them had, each of the pods which requested resources had 500 millicores set. So 450 should be within that. Well, let's just make sure I get that right. And then that was the first one.
Is that an API that you can read from the agent on the server you loaded, or?
That's in the
is that
resource.
the app that you developed?
This is the Kubernetes test package, the resource consumer. It exposes a HTTP interface, and then you can poke it to consume CPU, memory, various things. And then the last one. And then I'm going to spin up Prometheus so we can go in and we can actually look at it. And I wrote this earlier. Prometheus is the standard sort of monitoring tool for most of the cloud native ecosystem. This at the top is PromQL, and what it's doing is it's saying, just check how much CPU each of these is using over the last period of time. And let's go in. Nope, wrong way. Oh, so you can see I kicked off all 3. It gradually climbed up, and they're all sitting at 0.45, so 450 millicores, exactly what you would expect. And that first workload I showed you, the one which was labeled at risk, it has requested 0 resources. It is entitled to nothing. It is guaranteed nothing, but there's free space on the node, so it gets 450.
And Prometheus is a resource management tool that's bundled in the Kubernetes suite. Is that a third-party product?
It's an open source project. It's part of the Linux CNCF Foundation, and it's used for monitoring all over Kubernetes and sort of the cloud native ecosystem. So this is the happy case. Everyone is getting what they need. The node isn't overloaded. The question is then what happens when there's a spike, and what's actually going to impact the workloads? So let me, which one do I want to first? So the first one we'll show is the greedy one. So this is the one which, oh, whoops. So this is the one which is guaranteed 500, but has absolutely no cap on it. Now I'm going to increase it to 1,500. So between the 450 requested, by the other 2, the 1,500 by this one, the small amount I gave to Prometheus, because when I practiced the demo, I gave it nothing and brought it down. And then the kubelet, the node is now over capacity. Then oh yeah, perfect. I'm just going to give it a second. The slight staircase, the fact that it takes a little staircase up to the actual new levels, that's a Prometheus sort of artifact. It scrapes every 10, 20 seconds. So if you were to change the load halfway between two scrapes, it would look and be just average out to 450 for half of it and 1500 afterwards. I imagine it's going to go up to very close to the value. Let's see. It hasn't quite reached the top yet. Let's check I got the right number. But what you can see is we increased the load. Well, first of all, the simple one, the blue curve, the one which is limited, it requested, it's trying to use 450. It's guaranteed 500. It's completely unmoved. It's within its requests. It's not breaking the rules. The other two have changed. It has done nothing. The red one, which is the greedy container, the one with no limits set, has spiked, and it has used up all of the spare capacity on the node. And it's also taken resources away from the green container, which was the one which requested nothing. So what you can see here is if you don't set requests if you don't set CPU requests on any container, when it converts that into the CFS shares, it gets 0 shares, which means it is entitled to literally nothing. It is always last in line for any CPU. So even though the red one is way over what it's actually said it needs, it's way over its minimum, it still gets every CPU core available before the green one does. And that means if you have workloads with no request set, it can pull other workloads going rogue, can pull every single resource away from it, and there's no guarantee. Let's see. Okay. So that's what happens if you let workloads run in an unbounded fashion. They can go rogue, and anything which doesn't have request set can lose everything. So I'm going to reset this. Okay. So back to Prometheus. Second. Getting the resource consumer to start is easy. Getting it to stop is a little bit more of an issue sometimes. Okay. So I'm gonna scale it down. Then
You're saying stopping a container is lengthy sometimes?
no, just this specific one. It's like a testing tool. So like poking it here and there. Sometimes it doesn't do exactly what you expect when you expect it. Perfect. And then yeah. And to be clear, this is not the normal way you would look at Prometheus. Normally you would have longer term data store, you would have Grafana, you would have dashboards. It's just like for this purpose, it's easy. So just look at it from this point onwards. The red one is the one which is requesting 500. trying to use 450 has no limits, but it doesn't matter because the load in it is only 450 right now. The green one is the one which requests nothing. And then the blue one is the one which is limited at 1,000 millicores. So we just tried to tell it to use 1,500. And what's happened is rather than with the purple curve where it spiked all the way up to 1,500, it's gone to 1,000 and you can see the limits kicking in. And because the limits have kicked in, the other green pod is now fine because rather than one pod running away or one container running away and taking up all the resources on the node, it got capped and there was still enough left for everyone else. However, that red container, the green container, the one which isn't requesting anything, it's still working on borrowed resources. And if I was to increase the load on the other container, which actually had CFS shares, has actually set requests, all the resources would come off this. So even with limits set, if enough pods spike at the same time, anything without request set will run out.
Prometheus, like the industry.
So that was CPU requests and limits in action. The plan was to show memory as well and to show the difference. And the big difference between CPU and memory is CPU is what they call a compressible resource, where if you run out, you can just start throttling different applications and everything can stay up. Memory is incompressible. You can't take memory away from an application without killing it. So the plan was to show running extra memory, and then the one with limits, once it hits the limits, it will get killed. The issue we ran into is the resource consumer is it's consuming memory in a subprocess. So the subprocess gets killed and the container stays up. But next time, better demo. So that's how they work. But then the key question is, how should I actually use them? And our advice is at the bottom. You should always set CPU requests. You should always set CPU requests because if you don't, you're last in line and you can frequently end up with nothing, especially if other workloads have requested their resources poorly and it's just a very noisy environment. So you should always set CPU requests. You should always set memory requests, and we would advise setting requests and limits for memory to the same value. You could maybe argue that you want to set the limits a little bit higher so that you have a little bit of headroom in case you use too much memory, but all you're doing is delaying the inevitable, because if lots of people do that, eventually the node will run out of memory and then things are getting killed anyway. And then we would advise, do not set CPU limits. What's that? We can, yeah. CPU limits, if you should set them or not, it's a hotly debated topic. We would strongly come down on the side of don't. And we would say don't for two reasons. First of all, you're just going to waste resources unnecessarily. You're going to have leftover CPU. It's there. You might as well use it. And there's no risk of using too much because provided you set requests, everyone's going to get what they actually need anyway. And the other reason we would say don't set CPU limits, the way the CFS, the CPU scheduler, works in C group v1, actually enforcing the quota adds a lot of overhead and performance issues. So if you go in, there's certain types of applications where if you set the limits, even if you don't get anywhere near them, it can still cause performance issues and instability in the application. I linked to 2 talks. A few people ran into this. These are KubeCon talks from past years. A few people ran into strange things in their Kubernetes deployments at scale and traced it back after a few weeks to setting CPU limits. So we would strongly say don't. The reason some people would say you should is they say it's safer because that way you prevent if people aren't good about setting good CPU requests, then having limits might prevent one pod bringing down lots of pods. And it makes it easier to think about the system and reason about it because you can actually say, okay, it can't get more than this. But we would heavily suggest don't set them. So 1 sec. Okay. So that's the container level. And then the question is, as you move out from the container level, how else do the resources get used?
Is there an issue with limits, is it cost CPU to limit CPU?
Does it what?
You waste CPU or you spend CPU trying to limit the CPU?
I think it's more the latter. It's not even just that you're leaving it open, it's the process to go in, or like the way it actually does the limiting can cause issues. If I share the slides, I would highly recommend looking at the talks. It's a little bit detailed. That's why I didn't go through the details of how the CFS quota works, especially because we think people shouldn't be using it. But there's something in how the quota limiting works, which actually impacts performance. It is meant to work significantly better in C group v2. I don't know the details of how or why. But in theory, that is one of the things they say will be better. So interaction with other Kubernetes components. I have an architecture diagram of Kubernetes. The idea is that the components are separated into two types. You have the ones which run on the control plane over here, the API server, controller manager, etcd, and the scheduler. And then you have the ones which a copy of them run on every single node. So you have the kubelet, which is the agent which manages the different containers on that node. And you have kubeproxy, which does the networking. The two places that resources come in most heavily, obviously the kubelet, because that's responsible sharing out resources on a node, and also the scheduler, because it has to decide where to place pods, and it wants to place them where they'll actually get the resources they need. So first, the kubelet does a variety of things for resource management. It's the component which converts the configured requests and limits the Kubernetes concepts into the underlying Linux configuration for C group. It has a component called cAdvisor built into it, which monitors resource usage on the node and exposes that as metrics. That's the source of the data we were looking at before in Prometheus. And then when a node starts to run out of resources, the kubelet is responsible for evicting pods and trying to clear up those resources within certain guidelines. And a key concept when understanding how the kubelet looks at different workloads is quality of service classes. So who's heard of quality of service classes for pods? The QoS, quality of service. So it's not something that you specify, you never see it in the spec, but if you look in the status of a workload, the Kubernetes is auto-assigning these to every pod. And the way it works is you have best effort. So best effort has no requests or limits set. It's just, it will take whatever is left and it is the last in line for resources. On the other end, you have guaranteed. So these are ones which have set requests and limits for every single resource on every container, and they've set them to the same thing, which means they've promised that they will never, ever exceed the amount they say they need. And then in between you have burstable, which are ones which say, I need a minimum of this, but if there's more, I'll take it. So best effort, if you think of breaking the rules as using more resources than you're actually allowed, best effort is always breaking the rules, guaranteed is never breaking the rules, and burstable is everything in between.
Eviction of pods, how does that decide?
There we go, perfect. So it's two stages. So the way eviction works is in the kubelet config, like you were talking before about configuring how much the overhead is, etc. Another thing you can configure on the kubelet is when it would consider itself short of resources. So saying it doesn't mean that it's actually out of resources, just short and wants to try and reclaim them so that it doesn't run out. So the defaults for this are 100 megabytes. So I was planning to demo evicting a pod, but on an 8 gigabyte node, trying to get it within that was difficult. So what's going to happen is when it exceeds a threshold, and the thresholds are all on incompressible resources, so memory, storage, when it exceeds the thresholds, it's going to create a node pressure event. If you look in the status of the nodes, you can see if they have node pressure. And when it has node pressure, it's going to go in and it's going to evict. And the way it decides to evict is it says who's breaking the rules, who is using more than they've actually, whose usage is higher than their requests, and then it evicts based on that. So if you're guaranteed, you're never getting evicted. If you're best effort, you're very likely to get evicted. and you can set priorities on the pods to let them, to try and order them within that. But if you're running as best effort or burstable, it's always a risk. And at least with the eviction thresholds, which are the defaults, it doesn't start evicting till it gets to like 98, 99% of the node resources. And then it's very likely that it will be too late. And what's going to happen is the node itself is going to run out of memory. And once the node runs out of memory, it starts killing pods, because that's the only way for it to reclaim. And it has a calculation. The details of the calculation are in the Kubernetes sort of docs, but the way it actually works is it goes in and it says, okay, it prioritizes killing best effort, then burstable, and it never kills guaranteed. And then when it's picking between pods in those QoS classes, it's going to go in and say, okay, if I need to reclaim resources, there's no point reclaiming 5 megabytes when this one is the one which is wasting 400. So it kills people which are sort of higher above the resources they've requested. The difference between the two behaviors is that when a pod gets killed, it's going to restart on the same node. So if that node was too busy, this isn't going to fix it, because it's going to restart, it's going to start consuming memory, and it's just going to happen again and again. If you evict a pod, then it gets booted from the node and hopefully gets rescheduled elsewhere on a node which is maybe a little less congested. So there's a slight difference between eviction and just straight killed. And the other place that Kubernetes uses resources is in the scheduler. So the way scheduling works in Kubernetes, the scheduler gets a pod, and the scheduler's job is to say, okay, what node should I run that pod on? And the way it does, it's surprisingly complicated, but there's two main stages. First, it takes a whole bunch of nodes and then filters them down to ones which are viable and not viable. And then once it has the ones which are actually viable nodes, it scores each of those nodes on a variety of categories. And the one which has the highest score gets the pod. So the resources come in both stages of that. So first, during the filter stage, the scheduler will check that for a given node, will the pod fit on that node? So looking here, there's a lot of CPU left. There's not a lot of memory left. If you had a CPU-heavy pod which required no memory, there's a chance it'll fit on that node. If you have the reverse, there's no chance it's fitting on the node. So first, it filters out ones which don't fit. The next thing it does, it says, okay, one of the scoring rules is, if I put this pod on this node, how is it going to affect the resource allocation balance across the cluster? If the average CPU usage is 50% across all the nodes, if adding it to node A is going to make that node have 70%, it will say no, because it will say it's bringing it too far out of whack from the average. And the actual policies used in the scoring for the scheduler are configurable. So you can actually try and steer it in different directions for different use cases. So for the case I described, that would be least allocated. Put it on the node which has the least resource usage on average, and then get an even balance across the cluster. You can also do most allocated if you're running something where cost is a key consideration and you want to try and pack as many pods on the node as possible. So if you go with most allocated, if there's one which has a tiny bit of room left and one with lots of room left, it's going to put all new pods in that small bit of room as long as they fit. And then the idea is that then you can spin the node down and save money. And I didn't put it on the slide. I must have forgot. Oh, I did. It's at the top. The only thing which matters is requests. The limits are not used at all by the scheduler. Totally thrown out, just uses the requests. And if you don't set requests, the scheduler just has fallbacks. So it just has a number which is hard-coded, says everything which doesn't have requests, treat it as if it requests 100 millicores and 250 megabytes. And the reason is because my understanding of why they do that is because if they don't, the scoring doesn't work. Like there's no idea of most allocated, least allocated, etc. if all resources are free, because it not costs you nothing to put it on that node. But that means if you're not setting requests, you're also not giving the scheduler a steer, and it may put pods which need a lot of resources all on the same node because it has no idea how much they actually need.
Does the scheduler honor whatever you set to each pod on the YAML file? Or is that separate from the limits?
It'll honor the requests, because one of the filters is to make sure that there is enough spare capacity on that node when it looks at the requests to fit it. So it will honor the requests, makes no guarantees about the limits, which is why you shouldn't rely on having access to resources above your requests, because there's just, you're at the mercy of the other workloads running on that node.
So the limits are a soft limit, and then the scheduler dictates everything else.
The scheduler uses the scheduler makes sure that Kubernetes honors the guarantee. It looks at the requests, which is the only thing you're guaranteed, and finds a node which can meet that guarantee. And the limits aren't used. It's just the requests, the resources Kubernetes actually guarantees you, and the scheduler is a key part of meeting that guarantee, because it will not put you on a node which can't meet that guarantee. The tools that Kubernetes provides to help actually manage this. So hopefully people are convinced everyone needs to set their resources, otherwise it's just the Wild West. You should be setting CPU requests for sure. Maybe you set limits, maybe you don't. For CPU, probably don't. For memory, you should. But now you have a cluster with 200 namespaces, each with different workloads, which is not exactly a huge cluster. And you need to make sure people actually follow the rules. And what are the tools you can use for that? So the first one, which is built into Kubernetes, is called a limit range. So we work a lot with people who are sort of platform engineers, cluster administrators, and then these create them. And what it allows you to do is say, okay, for this namespace, if people haven't specified these resources, give them these as default values. And that way, even if people forget, you can give it to them and you can guarantee that they've actually set them. Can't guarantee that they've set them well because you've just picked a default, but at least they will be set. And it also provides the ability to set minimums and maximums. So you can also say, okay, for containers in this namespace, people can pick their own limits and they can pick their own requests and limits, and they don't have to take my defaults. But if they do pick them, they have to be between, in this case, 100 millicores and 1. So you can set defaults, you can force people to actually always have resources set, and you can put constraints on them. And then building up from that is, okay, so that's at the individual container level. What about beyond that? So the second concept in Kubernetes, which is used for this, is a resource quota. So it takes the minimum and maximum part of the limit range and extends it to, it provides a sort of aggregated view across the namespace. So the limit range, if you were to set, say I want 500 millicores, that would be fine. But you can still use way, way, way more resources than maybe was expected by just adding lots and lots of replicas to that workload. The resource quota will go in and say, okay, across this whole namespace, in this case, it says, don't let the CPU exceed 1,000. Don't let the number of pods exceed 10. You can set constraints on resources, requests, and limits. You can also set constraints on the counts of various Kubernetes objects. So if someone's using an auto, for example, you have a workload which uses background jobs to do various processing. If you want to limit the number of jobs that workload can spin up at any given time, because you don't want it just flooding the cluster with batch jobs, you could use a resource quota and say, this namespace can't have more than 10 jobs running at any given time. And you can configure separate policies for different priority classes. So if you wanted to have different priority classes for databases, API, machine learning workloads, you would be able to limit them differently, even within the same namespace. It's extremely flexible, though I strongly, strongly suspect that if you try to do this in practice, it would be the classic Kubernetes trade-off of, it's extremely flexible. You can do whatever you like, but it's going to be pretty complicated and take time to get it right. And then I have an example of that in action. So I'm going to delete all the pods I had before. Let me just look. I'm going to create a new namespace. And then I have a limit range, which has default requests and default limits specified. So I'm going to create that limit range and then put it in the limit range namespace. And then I have my workload, no resources specified at all. And then go in. And hopefully, surprising no one, you can see the container which was created, no one specified resources. The resources are set as expected. However, as I said before, I can still make that I can still, even though I'm limited to the resources in that container, I can still scale this up, add replicas, and I can take over the whole node. So if I do this, two new pods start. Why is it pending? Silly.
Resource this discussion.
Yeah, I did something silly. When I went to clean up the workloads, I deleted the pods, not the deployments. And then the deployments just spun the pods right back up. Yeah. So that's why they were all pending. That was the second part of the demo, showing how you have pending unschedulable pods if you run out of resources on a node. So I guess I did it anyway. So now we have, I'm surprised that that pod is pending. Yeah. So you can see if you describe the pod in the events, it can tell you this is an example of the scheduler filtering out all the nodes. So that filtering stage before where it checks if the pods fit, it has gone through and there's only one node, it's checked all of them and it says 0 of them fit. And then that's why you get the failed scheduling. And if you had the cluster autoscaler installed, then the cluster autoscaler would have responded to this failed to schedule event and would have started a new node and then this would have got scheduled, but it's a demo. I'm trying to figure out why. I know why. Let me remove Prometheus and see if it gives it just enough space to. There we go, running. There's enough space and it got scheduled because I took down another workload. So scaled up, each of them got the defaults of 500 millicores. That's fine. So let me scale it down. I'll scale it down to 1. Okay, scale it down to 1. And then let's show the resource quota. So the resource quota, simple, just compute resources. It says don't let objects in this namespace use more than 1200 millicores. So that means should be allowed 2 pods, should not be allowed 3 pods, because if each one is 500 millicores, 3 will be too big.
These resource quotas for every pod, every container on the.
So what's the question?
The resource quota?
Yeah.
For what? Like
Namespace. Yes, so what it's going to do is it's going to sum across all of the pods in that namespace and make sure it meets the quota. So before I scaled up to 3, and I was using 1500 millicores. I'm going to put this on, which says you can't go above 1200. I'm going to try and do the same thing again, and it's going to say, no, like, do not pass go, do not collect 200 pounds, dollars, just not allowed. So scale it up to 2. It's all good. Scale up to 3. Still 2 pods. It's not allowed. And actually finding the error took me a little bit of time. But if you go into the replica set, so the Kubernetes object, which is responsible for starting and stopping replicas, and you go to the bottom, you can see error, can't create pod, exceeded quota, maximum resources, CPU. So as expected, it works. So I think I covered this earlier. The key points to take away, the thing which really matters is requests. That's the thing which you're actually guaranteed to use, you should rely on, and the thing that everything else in Kubernetes is keying off. The scheduler doesn't use the limits. The kubelet doesn't use the limits. Everything is focused on the requests. So you need to set them, and you need to set them right, otherwise it's going to be chaos. Because if you set them, but everyone sets them too low, then everyone's going to exceed them, and everyone's going to get throttled. Limits are a tool which you can use here and there. We would say they're most useful when you've not bothered to set your requests right, because that way it provides a fail-safe so that even if you haven't set your requests right, one pod can't take down all the other pods on a node. And then the question is, so you need to set requests. What does it actually look like to do that in practice? So we see the same journey again and again and again. Everyone starts, they don't think about requests, they don't think about resources, they don't set them, and it's fine until you get some serious load, and then everything breaks. You have performance, reliability issues. And then you're like, okay, well, we need to start setting requests, resources, requests. What do we set them to? And unless you have done significant benchmarking, etc., it's a hard question to answer. And the easiest approach is one size fits all. So say, okay, everyone gets 1 core, whatever it is, 1 gigabyte of RAM. And it typically works. Everyone's getting resources now. And you won't have performance problems, which is great. But cluster utilizations we see, I think the average cluster utilization is like 25%. Because if it's one size fits all, for this to work, you have to give everyone the resources that the biggest workloads need. And then all the minnows just waste those resources constantly. So you do that, and eventually the cloud bill grows and grows and grows, and you know that the resource utilization is terrible. You know you can save 2/3 of the bill, and you're like, okay, we're going to do it properly. And then what doing it properly typically looks like is accepting that every workload has different resource needs, and you need to set them individually. So people go around and they try and get the developers to do it on a case-by-case basis. And it can work. We don't think it does often because the process and the effort required to do it properly and the tooling is painful. And it's just very grueling to try and get people to do these manual tasks every day, every week, every month. But in theory, it can work. It's just not a great use of resources. I know no one likes to be pitched. Our product does it automatically for you. The idea is that you have all of the data coming out of Kubernetes to do this with machine learning and pick the right levels so that every workload gets the right resources, and then Kubernetes provides the automation to patch them on an ongoing basis. So the idea is you get all of the benefits of stage 3, you get high cluster utilization, you get better reliability, but you don't waste huge amounts of time doing it manually. And it's just something you can stop thinking of. And I put the link at the bottom. I'll share the slides. We always love feedback, having people try the product, sign up. It's a one-click install. You install a Helm chart, and then we do the rest. So it takes 5 minutes. And if you do install, email our product team because they always love to hear the feedback from your users.
Is there a best practice?
For using our product,
You know, using, regarding the law and the request and setting the limitation of CPU and memory.
I think maybe I went a little too fast. Always set requests. Always set requests for CPU and memory. Do not set CPU limits once you have your CPU requests set appropriately for the majority of the workloads in your cluster. And with memory limits, I personally would set them to be the same as the memory requests. That way, if a single pod starts to go rogue, it will get killed before it impacts anything else on that node. But if you like the idea of maybe some pods being able to burst a little bit, maybe you give them a little bit of leniency. So you could set the limits a little bit higher than requests, but they should be pretty close, pretty close.
I think I heard you say memory requests, is that the metric for requests?
No, that's the requests you put in the YAML for the memory resource in each container.
So request is tied to the memory consumption. Or
The re-
assignment.
So requests is the minimum guaranteed resources by Kubernetes. And when you set it for memory, it says, okay, this container will get at least this much memory.